For those of you who weren't in the morning, you saw, in addition to all these amazing accolades, I also wrote the book R for Everyone. So a lot of the stuff you're seeing today can also be found in R for Everyone if you want more exposition on it. So, for those over here this morning, where did we leave off?
Elastic net.
The elastic net. We had just finished and made predictions on it, on new data, otherwise known as scoring, or God forbid as inference, which is a totally terrible name, but we have to live with it occasionally. So now we'll take just a moment while my computer decides to open up programs and such. Seemed like this happened this morning, didn't it? It's moving slowly, so we'll give it a second. Do we have any questions from this morning while I try to get my computer up and running? Yes, hand in the back.
How does one choose the optimal number of folds for the cross-validation? Because if I change the number, I get the number of parameters for the one SE ranging from 10 to 20.
So the question is, how do you choose the optimal number of folds? So first, let's unpack your question a little bit. So the first thing is, each time you're changing it, you're actually doing the randomization differently. So it's not, that doesn't necessarily have to do with the number of folds you chose. It has to do with the randomization. Because if you even did 5 folds repeatedly, you could get different answers back. That's why sometimes people will do repeated cross-validation. So you do a 5-fold, you do another 5-fold, another 5-fold, another 5-fold, and that makes it more stable. Because already you're having some issues. Then you get to the question of still, how many folds should you do? The 3 most common are going to be 5-fold, 10-fold, and leave one out. Leave one out is where if you have n data points, you have n folds. That's great on smaller data, but prohibitively costly on larger data. So let's assume we don't want to do n-fold cross-validation. So then we're left with really 5 or 10. 10 is nice. But you can get away with 5. So Hasty and Cipriani, the people who wrote GlibNet, they've done a lot of other stuff, by the way, besides GlibNet. I believe they came up with generalized additive models. I don't think they invented splines. I think they just used splines and GAMs. They came up with an algorithm called RuleFit. I believe one of them, if not maybe Friedman, came up with gradient boosted machines. They've also came up with a gap statistic for clustering. They've come up with a lot of the modern machine learning that we have today. And they wrote a paper, and I read this about 10 years ago, about how many folds is optimal. Because at a certain point, you need to balance computation with accuracy. Theoretically, the more folds you have, the better analysis you can do. And I remember reading a paper where they said 5 folds is good enough. They did a lot of experiments, a lot of simulation, and they found that doing 5 folds gave them accurate enough results. So I just sort of go with 5. It's a nice balance between accurate enough and not too computationally taxing. 5 or 10, you'll be happy. Yeah, there is no one right number. It's not like 7 is right. Yeah. Any other questions while I wait for my computer to reboot itself? No, we're not even rebooting it. We're actually trying to get to the point I can reboot. Yeah. Yeah, so it's github.com/JaredLander/ODSC London 2018. So I'm going to do a quick reboot because my computer just doesn't want to respond. It will respond to being turned off, though. And it's amazing how you solve so many of life's problems by rebooting your computer.
Or getting it back.
Nah, that just causes more problems. You're essentially paying for a free OS. Just think about that. They're using Unix. So you're paying to essentially have Linux. Just use Linux for free at that point. But I will say on Windows now, they have full integration of Linux. There's a Windows subsystem for Linux. It is amazing. I highly recommend it. Right now they have Ubuntu, SUSE, and even Kali. There's Kali Linux on Windows now. Think about that for a second. Who knows what Kali Linux is? No one? So all the hackers use to do pen testing, that's available as a Windows app now. If the pen testers are willing to use Windows, it's come along.
So you just download the VM and go.
No VM. It's just essentially an app. It's a full-fledged Linux, shares resources, no VM. yeah.
manifests itself as an app to Windows.
Yes, so it's contained in an app, but it's a full file system, full everything, but it's not a VM, so it's a fully integrated part of the system. You don't need to allocate memory or resources or anything.
And you download it from
The,
Microsoft,
the Microsoft Store?
and it comes preloaded with the working Linux.
Yeah. It's pretty amazing. I can't stress enough how amazing this is to have now. I do almost my entire workflow on Linux now on Windows. So,
I wonder if it'll run on the Windows VM on my Mac.
oh wow. Getting very meta now. All right, so my computer is just about booted. So now we are going to get into a new class of functions. So if you recall, and I will bring it up in a second on my screen, the equation we are doing is y equals f of x. I need to find a better place to put this water bottle. Here's 2 slanted, and here's 2 blocking the camera. Next thing you see a bunch of water being spilled out everywhere. All right, so I'm pulling up RStudio, and look at the font is incredibly tiny. All right, let me just pull up something else for your benefit. I'm gonna pull this up. Just give it a moment. It's just coming on online right now. And I will make the font bigger because you cannot read. Actually, no, this looks pretty good now, doesn't it? You'll tell me. That's the same as it was before. All right, I think we're good. So I'm going to open up a new file. That's the first step I'm going to take. Then I'm going to just pull up something on my screen. Give me 1 second. I know we're getting started here. Are we all out of questions now? Everyone's good? Sorry, 1 more second, folks, then we'll be all set to go. Huh, I never saved that file, I guess. I'm just looking for a file that would make some life easy for us. Okay, so let's get started. We'll go back to our Markdown document, which is all the way over here. And you'll recall, we are simply trying to fit y equals f of x, right? Your output data is some function of your input data. So far, we've looked at a linear function. And it means linear in the coefficients. It doesn't actually mean a straight line. You can have a curvy linear line for this stuff. Like, if, for instance, if you put a square term in, that would cause you to have a parabola. You could put a cubic term in there. It is entirely possible to have nonlinear relationships in a linear model. But we want to actually get into a nonlinear model where there's not a multiplicative effect from the outcome to from the input to the outcome. And we're going to focus on trees. So who has used a tree before? Who knows what a decision tree is? Thumbs up, thumbs down. So it seems like everyone here knows. I see a few sideways. It's essentially, you're essentially binning your data into lots of little bins to figure something out. Let's say I wanted to figure out the average height of this room. I could just go around the room, take everyone's height, and compute an average. Simple average. But we could probably do better than that. We could probably also include a variable for your age. We can include a variable for your sex. We can include a variable for your hair color, and develop a linear model. Or we could divide you up a little bit. So first what I might do is I'm going to take everyone in this third of the room, compute your average. Then this third, compute your average. Then this third. And already I've broken it up. I now have an average for each individual group. It's a conditional average, which essentially is what a regression is on a continuous scale. But then I want to say, OK, I want to say the average height for the people in this room under 18. Probably not anyone here, I'm guessing, but let's just go with it. And the average height of this room for people here above 18. Here, I'm going to do the split, people below 16 and above 16. And over here, below 25 and above 25. So I'm getting granular. Splitting you by geography probably didn't make much sense for your height, but none of this is going to make much sense. Now let's say I come over here, under 18, over 18. Are you wearing a blue shirt or a non-blue shirt? Over here, are you wearing glasses or are you not wearing glasses? over here. So essentially, I'm creating lots of little buckets for this room and taking an average height for each bucket. It's sort of like a marketing report. You know, people aged 25 to 34 who drink Coca-Cola like your band. You see a lot of those things. How do these marketers come up with their buckets? They just things that they've been using for decades and they've stuck with it. All we're doing is creating buckets and taking an average in the bucket. The difference is instead of sort of putting our finger in the air to figure out what the bucket is, we're letting the computer decide optimal bucket splits. That's all we're going to do for a decision tree. So the way this looks is like this. Let me pull this up for you. I'm just going to pull it up in a talk rather than write it out. How about that? Make it go a little faster. But wasn't that cool the way I made those equations?
Yeah. Very cool.
Yeah, I think that stuff's great.
I was thinking the man can think in LaTeX.
LaTeX is very incredibly powerful.
That's what it is, isn't it?
It's LaTeX math in a markdown document with live previews. Yeah, amazing stuff that the RStudio team has given us. So let me pull up the math here as I wait for this very slow slideshow to load. You know, I'll come here in the meantime. Maybe I will do some math for you, so I'll just read off the equation.
Even more amazing, the underlying code is probably older than you are.
For LaTeX? Oh, yeah. Oh, yeah, that stuff's been around forever. What, it's at least 40 years old, 50 years old maybe?
I think the tech book is from the early 80s.
All right. Oh, come on, give me this. Okay, decision tree. We could actually do this. So, the formula for a decision tree, you're estimating a function. So the function we are estimating, it's an estimate, so we'll say f hat is equal to the sum of m equals 1 to capital M. And then if we were taking a height, as we've been doing, it would be C underscore M. Nope. That looks better. Times the indicator of X is in the reals. And I'm sure there's a better way to make that R. What is it? Slash R? We'll just say R, right? RM.
Slash script, isn't it?
Probably, but then I realized I don't want the script, actually. I was thinking of the real numbers, but that's not what it means. It's a region. So essentially, what we're doing is we're breaking our data into M regions. Remember, my rooms, my heights, my columns, my heights, my glasses, my shirts, right? Breaking it up into M regions. And for each region, the function is becoming the average. The C here stands for average for an individual region. So you're either in a region or you're not. So you are in a region where you're on this side of the room. I'm going to guess you're over 18. You're not wearing a blue shirt, right? So you're in that one group. So you would get the average for all the other people over 18, not in a blue shirt in your area, okay? And that average would be for everyone. That's your average height. Trying to see, you are here, you're over 16, you're in this region, you're not wearing glasses. Your predicted average height is the same as everyone else's. Make sense? That's for a continuous variable. If you'd had an outcome variable, if you had a categorical variable, it would just be the number of you. So let's say, what's categorical now about a condition I can find here? Light hair versus dark hair. Male versus female. So let's go around the room, not go around the room, but the probability of someone being a male or a female. Well, no, we're not supposed to have gender, binary gender. So let's go with dark hair or light hair. I don't want to go into any territory. So light hair or dark hair. I'll split up the room. And let's say we only have two classes, light hair or dark hair. All right? And this side of the room, for all the people on this side who are over 18 in blue shirts, I count the number of people with dark hair divided by the total number of people in the group. All right. Let's come to this side of the room. I find all the people in this part of the room with no glasses. I count the number of people with dark hair, divide by the total number of people in the room. And it's essentially a vote. Does that make sense to everybody?
In the room or in the subgroup?
I meant right here in this subgroup, in this tranche right here. Yeah. So the n, the denominator is just for your group, is the number in the group. Now let's say we had a multivariate thing. Now let's no longer say dark hair. Let's say dark hair, blonde hair, red hair. Does that cover? Let's just say there's those three, all right? So I'd come here, I do the number of dark hair divided by everyone in this group, the number of red hair divided by everyone in the group, the number of blonde hair divided by everybody in the group. And it becomes a distribution. That's classification. It's just majority wins. That's all that is. And when I say decision tree, a lot of people think the decision is based on the outcome variable. Like, oh, you can only do this with categorical data. No. A decision tree can work on numeric outcome data, on binary outcome data, on multi-class outcome data, and might even be able to do count data. The decision part of the decision tree is asking the questions on the input data. It's about creating those splits, where you're making a decision on how you split the data. All right, that's where the word decision comes from. So that's why it's often called, one of the first algorithms is called CART, categorization and regression tree. It was always meant to do both from the beginning. And they realized that this looks like a decision tree, like in a management style decision tree. So let's take a look at how to build one of these. So we will start off in a new file. So I'm going to do Control-Shift-N and make a new file. You could continue in the file from this morning, but I'm going to keep things organized. That one was called Glimnet. This one will be called XGBoost. And I'm going to load up some packages we need. For instance, we need useful. We might need coef plots. I'll load it just in case. We are definitely going to need XGBoost. We are likely going to need magrittr. And we'll almost certainly need digraphs. And if you installed coefplot and useful earlier, then you should have digraphs, and that will give you magrittr for free. And XGBoost, if you haven't installed it, go ahead and install it. And I need some data. So I'm going to read in the same data I read in earlier. Read RDS. Data / Manhattan _ train. Now you might be saying to yourself, well, if we're continuing in the same session we had earlier, why am I reading in the data again? Is anyone else wondering that? You're not wondering that? So each file, you're in the same R session. This console, if you didn't restart your computer like me, you have this data loaded. So theoretically, you don't need to load the data again. The reason I am loading the data again is because I want this file to be self-contained. If you come back and look at your notes 2 weeks from now, I don't want you to come to the XGBoost file and be like, hey, I can't run this. Oh, I need to go open up the Glimnet file. This way the files are self-contained. It's better for education purposes. Normally, if you're doing analysis, you'd load the data once. Educationally, I'm loading it in each file. I'm also going to load in the test data in case we get around to doing that. That's Manhattan test. And I'm also going to load in land val gets read RDS data / Manhattan validate.rds. Okay, everyone's good so far? Now, instead of doing regression, we are going to do classification. This way I could teach you something different. You absolutely could do regression here, but I just want to make sure you get variety from today. And also because, let's be honest, when people talk about AI, 95% of the time it's just a logistic regression. That's if it's not an if-else statement. Did my font just get smaller?
Yeah, it did.
Somehow.
You know what? All right, hold on, give me a second here. Sorry about that. Better?
Yeah.
All right. Give me 1 second then.
Can we set the seed now?
Yes, we can. But it's going to quickly get out of hand because I'm going to run something. I'm going to run it twice. You're not going to run it twice. It will get out of hand. I'll set it just for good measure, but it's going to get out of hand really quickly. Just give me 1 second to pull up something. This way my font won't get out of whack. All right, wonderful. All right, cool. So let's set the seed now, but it's going to be like trying to bail out the ocean. If you want to make sure you get the same random results, you can set your favorite seed, whatever your favorite seed may be. Though someone has been doing some research lately discovering that not all random seeds are valid. Especially 42 is not a valid random seed. Right? Isn't that awesome? When I saw that, I'm like, that is perfect. That's not valid. For those of you who don't know what 42 is, you're not nerdy enough. Just Google the number 42. All right. So, but again, as soon as we start running different commands, they're going to be out of sync, but you'll have it going forward. I want to look at a variable called historic district. So I'm going to say table of land underscore train. Train dollar historic district. Basically, this is a value saying, is the district historic? Is it not? If it's historic, you can't build anything and prices skyrocket. If it's not historic, you can develop. And often in New York City, it's very controversial making something a historic district because people think you're saving the neighborhood. But in reality, you're making it so expensive that no one can live there. And it's nice to look at, so it became a museum. I can't imagine London has that problem. So in our data set, it's either no, it is not historic, or yes, it is historic. Notice we have about 24,000 not historic and 8,500 is historic. If you're fitting a machine learning model, you want those more balanced. So you probably downsample your data. We don't have time today to downsample your data, but you would want to do that if you're doing this properly. And if you want to do it properly, there's a package written by Max Kuhn called rsample. Check out rsample for downsampling, but we're going to skip that for now. We are going to need, however, to come up with a formula. So we're not going to use the same formula as before. So you know what that means? A lot of typing. Or I'll just save this file and you can go ahead and copy and paste. So I'm going to save the file as code, well, as XGBoost in the code folder. And I'm going to go open up a terminal and save it for you. I'm just doing I'm doing it off screen, so this way it will, I don't need to put in my password every time. Okay, if you go to GitHub now, you can go and get this file and copy and paste this. Does this look familiar to you? It's very similar, but the difference is, instead of using total value as your outcome, this binary variable, historic district, is your outcome variable. All right? We're using a lot of the same predictors, including I think, total value. Did I include total value in here? There it is. Thank you. And I'm still subtracting the intercept, because trees don't need intercepts, so I'm getting rid of the intercept. All right? And now there is debate when you're building a tree. Should you leave your categorical variables as a factor, or should you convert them to dummy variables? Because in a tree, you don't need them to be dummy variables anymore. Trees behave differently. So again, Max Kuhn, I talk about his name a lot. he did a whole study on this, and he presented it at the 2016 New York Art Conference. There's a video available. It's titled, "I Don't Want to Be a Dummy." And he said, when is it better to convert it to a dummy, when is it not? And for the most part, it didn't really matter. There are a few edge cases where it did matter. But with XGBoost, we have to make them into dummy variables because XGBoost is designed by computer engineers, not data scientists, so they don't let you do it the fun way. Sorry if anyone here's a data engineer. But you're boring. No, kidding, sorry. All right, so much like before, we need to build our X and Y matrices. Remember we built those earlier? For those of you who are here. So we're going to create, again, land x underscore train gets build.x. Now, if you're still running from earlier today, when we do this, you're going to overwrite your old land x. Hope you're okay with that, but thankfully it's code, so it's reproducible. You can just rewrite another code. So we're going to put in here historic formula, which I never created. Oh, hist formula, that helps too. Hist formula, comma, data equals land underscore train. Contrast equals false. We don't need contrast for a tree because it doesn't care about collinearity. You're not doing matrix algebra anymore. And sparse equals true. Likewise, we'll recreate land y underscore train. And we'll do build.y. Please don't forget that we're doing y now. Hist formula. Data equals land underscore train. And that's all we need. There are no other arguments to build.y. Except if we look at the head of land y underscore train, we are going to see that it is a categorical factor variable with no as the first level and yes as the second level. And this works great for just about every modeling function in R except XGBoost because it's written by computer engineers. They don't want a factor variable. They don't want false and true. They literally want the integers 0 and 1. So we have to take our data here and convert it into a integer. So after build.y, we're going to put in a pipe. And I'll drop to the next line. The pipe, if you haven't seen a pipe, you really need to use pipes in R. It's life-changing. We're going to pipe it into as.integer. And if we do that, we can see, it's only showing us the first few. If I do n equals 100, yes became 2, no became 1. Because no came first, yes came second. So in R, factors are technically integers underneath the hood with just pretty text on top of them. And they're literally stored as 1, 2, 3, 4. However, we're not done. Because XGBoost doesn't like 1 and 2, even though it's still binary. It insists it has to start at 1 and be 0, 1. So we need to, after as.integer, do minus 1. And now if we look at the head, we have zeros and ones. Mathematically, they're the same thing, but they insist on 0, 1. All the user-friendly stuff went out the door. Use caret if you want to be user-friendly again. All right. Bless you. Everyone got that? Let's do the same thing with our test and validate data. So I'm just going to copy and paste to save some time. I'm going to paste it twice. And I'm going to do test. And I'm going to make sure this is test. Oops. I totally copy and pasted in the wrong spot. Here, I'm going to just make sure it's right. There it is. Test. It's hard when you look over your shoulder. And the second one, instead of train, it's going to become val. And I will use the validate data. OK. So let's make sure we got that right. We have land x and y train, land x and y test, land x and y val. So you might be used to the whole training and testing. You train your model on the train data, and you see how you did on the test data. Well, there are some algorithms that let you see how you're doing along the way. So for that, you need a third part of data called validate, which is just like the test data. You train on your training data, you see how you're doing on your validate data, and at the very end, to test all your behavior, you test it on the test data. We didn't need this with GlimNet because it did cross-validation, validate. It handled the validate part for us. With XGBoost, while it does do cross-validation, it's not super clean for what we want to do. So we are going to have this held out validate data set to see how we're doing along the way for our parameter tuning. Okay? Does everyone make sense why we have the third data set? Okay. So, now that we have our data ready, we are almost ready to begin using trees. But once again, XGBoost wants things in a certain way. Instead of passing x and y to the XGBoost function, we need to pass a special XGBoost object. So we need to create that. So we're going to say xgtrain gets xgb.dmatrix. This is creating a special object that holds both the x and the y object simultaneously. So we say, using terminology clearly designed, by engineers, sorry if I keep taking shots at them, data equals land x underscore train, label equals land y underscore train. Clearly they weren't thinking about continuous outcome variables when they built this. Like, oh, everything's a classification problem. Oh, no. Did I get it? Oh, I know why. That's because I ran something the wrong way. Test and test. All right. I ran my things out of order. It happens. I make errors too. That's how I learned to get good at reading errors. All right, everyone built XGtrain. All this is, it's almost like a list holding two objects. And this will allow XGBoost to iterate through the x and y's row by row automatically. And I'm going to copy and paste down and create this for the validate data. XGval gets land x underscore val, comma, label equals land y underscore val. We're not going to do it for the test because if we get around to doing predictions, we don't need the y data, so we're not going to do it for the test. Okay. Everyone good? So let's go ahead and fit our first model. Traditionally in R, if you wanted to fit a single regression tree, you would use the rpart function. Rpart stands for recursive partitioning, and it works great. We're just going to skip ahead to doing it with XGBoost. So we're going to say xg1 gets xgb.train. And I'm going to skip to the next line. I'm going to say data equals xgtrain. And now we have this ambiguous usage of the word data, right? Because when we did xgb.dmatrix, data was the predictors. But now in the training function, the data is both the x and y combined. It's just terrible terminology. Good thing it works well and it's fast. We then specify an object. Oh, nope. It's typing the wrong area. We then specify the objective. This is what you want to accomplish. It's very similar to the cost function. When we did GlimNet, we said Gaussian. If we were doing this in GlimNet, we would have said binomial. In XGBoost, you say binary colon logistic. Logistic regression is a type of binary regression, and it uses the logit to transform things from the log-odd scale into the log-odd scale. Don't worry too much about it for now. Just know that this is how we tell it. We are going to do a binary outcome variable. Remember, this is for the outcome variable. Could you speak louder? Then you would do, I believe it's like it's linear colon regression or something like that. I forget the exact thing, but it's like linear colon something. The help menu has them all listed. I just don't have that one memorized. We could look at it later. We probably will if we have time. And lastly, I'm going to say n rounds equals 1. Don't forget to close your parentheses. And it ran, it's done, because it's fast and we only did one round. Kind of anticlimactic. So we have built a tree. If you don't believe me, let's see the tree. We're going to say xgb.plot.multi.trees. We're going to give it the model xg1. And we're going to tell it the feature names are the call names of land x underscore train. So this is a function which takes in a model. Now, however, XGBoost doesn't keep the column names in the object, so you need to manually specify that for the plotting function. And even though we only fit one tree, we still have to call the function multi-trees. And when we do that, I'm going to zoom in. I'm going to obscure the code for a few moments. We get a tree. It literally looks like a tree. You ask a question, and they answer yes, you go this way. If they answer no, you go that way. Once you answered yes, you ask the next question. Yes, no. Next question. You recursively ask questions all the way down the line. And this is the decision. You ask a series of questions to get to your final bucket. And that final bucket, in this case it's binary, you count the number of yeses, divide by the total number in that bucket, and that's your answer.
Where in the code was the numbers or the whatever from the decision?
What do you mean?
So there is a decision to split.
How does it make the split? The algorithm figures that out. You don't decide the splits. You're not writing SQL queries in the 1990s. You're letting the computer decide the splits for you, and that's the magic.
How do you know how many levels?
How deep did it go? Great question. So by default, the maximum it can go is 6 deep, by default. Now it can decide to stop earlier if it needs to, but it can never go further than the maximum you allow, which by default is 6. And we'll talk about hyperparameters if we have time a little bit later.
Is there a law of nature that says the only way to do this is a plane around with the axes?
Oh, could you rotate it, you mean?
Well, could I split along a linear combination?
Can you split along a linear combination of inputs? A tree can only split one input at a time, and it can only make it a binary split.
But you can calculate the linear input.
Right, if you had made another variable that was a linear input of other variables, it could split on that new one.
Is the one that will do it for you in an optimal sense?
Yes. It won't build a linear combination optimally, but it will split whatever combination you build. You can do any sort of feature engineering you want, and then have it split on whatever fabricated variable you make.
So sorry, I'm kind of saying. So if you can you have 3 splits?
Right.
1
So,
to 3, you can't do that.
oh no, you cannot. Each split is a yes or no question. So let's say you have a continuous variable like your height. It will say either above 25 or below 25, and it splits you into 2 groups. It could then ask again, you're above 25? Okay, are you above 35 or below 35? And it can keep splitting the same variable, but at any one given split, it can only split once.
Like a recursion of a fashion.
It's a recursive splitting.
So you had like, which city you come from?
So let's talk about the color of your shirts. Blue, orange, green, black, red. Let's just call it that. So there are 5 different colors of shirts. So we can ask a question. What color is what bucket? Well, let me say this back. You can ask a question, is your shirt blue or everything else? It could also ask instead, is your shirt blue or orange or everything else? It could also ask, is your shirt blue or red or everything else? So it will actually consider all 5 2 to the 5th combinations when it's making a split.
Would it make a difference which one comes first or second?
No, because we haven't really talked about how the tree splits, but basically at every step of the way it asks, let's say you have 10 input variables. It considers every possible split for those 10 input variables. For the continuous input variables, it's easy. There's a mathematical formula to find the optimal split the first go around. For categorical, it cycles through all the combinatorial options for each categorical variable. And it decides, OK, for this stage in the data, splitting this variable at this point gives me the optimal split so far. Then it goes on each branch and finds, OK, let me search all the variables in this branch. Let me search all the variables in this branch. Ask more questions. Then it can go again and again. Each step of the way, it can only have a left or a right-hand path. It can't be a tertiary path.
Isn't it? When I first started looking at that, I think of it as simple as, so if we use the shirt analogy, you're blue, you're not blue. And you basically, I think of buckets, which are branches on your tree. And if you like, they're not terminal nodes, but they're nodes. And then you go, well, we've covered the blues, so you're orange, you're not orange.
That's possible. But it could even ask the question at one split. Are you blue or orange,
Yeah.
or are you red, green, yellow? And it can actually have multiple categories on each side of the branch. It doesn't have to be just one category.
Which
Yeah.
is more effective or efficient, or does
It does it all.
the package just does it?
It figures out
behind
the-
scenes for us.
It figures out behind the scenes.
So I don't understand what's the objective when the computer is splitting. What's the objective? How?
It's trying to get to the point where down in the terminal nodes, whatever the answer for that group, let's say there's 20 people in a terminal node, it wants to get as close as possible to the reality in that terminal node.
But then it's not iterative. It's all of that division together.
No. So right here it asks you one question, then asks another question, another question, another question.
So how do you know at the first node how to make the division, given that there are many others following?
So what it does is, let's say you have 10 input variables. It checks all 10 and says, at this stage for the first question, which of these 10 give me the best split right now? Then, after you've made that split, it then says on each branch, which variable out of all of them will give me the best split right now? And at each step of the way.
Sequential is better than simultaneous.
It can't do simultaneous, really. It's a recursive tree. You go down the tree.
We can revisit variables.
Yeah, so I could ask you first your age, then ask about your shirt color, then within there, ask about your age again. You can even ask about your age, then your age again right away to come up with multiple splits.
Yeah, so what do you mean by best fit? Like the optimal meaning less entropy?
More information gain. And I believe it uses the Gini index traditionally. And it tells you how much information. Did I pronounce that right too, by the way? Is it Gini or Gini?
I think we said genie.
Gini.
Yeah, you got me thinking now.
The GINI index.
Yeah.
And it uses that to figure out how much information is gained. And that's a measure of how much extra knowledge you would get by asking this question.
I forget, is it the higher the Gini index, the better? I forget.
The higher the index, the more information you gain.
Thanks.
Yeah. And so every tree works that way in some form, regardless of the algorithm used. It searches all the variables and all possible splits of each of the variables at each step of the way, splits it, then continues down that path. And now, think about combinatorially, that's a lot of things to search for, but somehow it's incredibly fast. These algorithms, the CART algorithm was written in the 60s or 70s, I want to say. And XGBoost is relatively new, and it's just an iteration on top of all these old ones. And there was CART, there was C4.5, there was a whole bunch of different versions of these things.
I know it's depending on what you're doing, but how is it a lot better than random forest?
Question is this better than random forest? Well, this is one tree. Theoretically, a forest is just 1,000 trees. Well, not theoretically, that is what a forest is. So the question is, what is better? And which leads us to our next topic. This is one tree. What if I change the data a little bit? I might get vastly different splits. While trees are understandable, because you could actually, this is a decision, you walk your way down, and they're highly understandable. But they're also highly variable. And when you're doing predictions, you want to rein in your variance. You want to have stable results. So one of the first ways to improve upon a single tree was to do a random forest. So a random forest said instead of one tree, let me build 500 trees randomly. Not completely randomly, but I'll talk about the random part. And then average all the results. Therefore, a tree that does well on this side of the room, but poorly on the other sides, will be averaged with a tree that does better on that part of the room. Will be averaged with a tree that does better on that part of the room, et cetera, et cetera. And it's literally, you're creating a forest of trees. The random part comes that when you build a tree, you have to keep making these splits. When you build one tree, you use all the data. When you have a random forest, within each tree at each split, you randomly sample the rows and you randomly sample the columns. And that ensures that each of your 500 or 1,000 trees is bound to be different. Now, a random forest is your first example of an ensemble model, taking multiple models and putting them together. It's a form of bagging. It's bootstrap aggregating. And random forests are great, and they were the rule of the roost. Is that a saying? Rule of the roost? They were the greatest prediction algorithm for a long time. They were still fast, completely black box, but they worked really well. If you were into Kaggle, you're probably using random forest for a while. But then they just learned about this thing called boosting. Now, boosting works it's most famous for trees, but it can boost anything. In fact, it was Haister, Tibshiriani, Friedman, some subset of those, came up with GBMs, gradient boosted machines. They boosted linear models, they boosted trees, they boosted whatever they wanted to boost. And I have a formula for boosting, which I will pull up. And what boosting does, and let's just talk about boosted trees, but everything I'm saying about boosting works for boosting a linear model, works for boosting anything. You fit a model, you see how well you did. You then use that to adjust your weights for the next model. And there's two ways to think about this. Let's say you fit a model. You could just say the next model is fitted on the residuals of the first model. When I say the residuals, it is the error between the true y's and the predicted y's using the training data. You get the residuals, and you fit another model. You get those residuals, fit another model. Get those residuals, another, and you keep stacking on top of itself. Other people like to think of this as in terms of weights. You fit a model, and then you check the residuals to see how poorly the model did, and then you either upweight or downweight the rows for the next model. You fit another model, you upweight or downweight the rows again. Another model, adjust the weights. Another model, adjust the weights. Both accomplish the same thing. Some people find it easier to think about the residuals. Some people find it easier to think about the weights. Mathematically, it looks like this. And again, this works for any function, doesn't have to be trees. You're predicted for y, for your ith observation, at the teeth tree. Is equal to the sum of all the trees. And for each tree, it'll actually be any function, not necessarily a tree, but we're just going to say the word tree. So essentially, you're fitting a function, in our case a tree, on your data, and you're fitting another one which learned from it, another one which learned, another one which learned. They're additive trees. A random forest, you fit 500 trees separately, completely independent of each other, and you average them together. A boosted tree, you grow one tree on another. So if you grow a stump and another tree on top of that, another tree on top of that, another tree on top of that. And it's called a stump because typically you do shallow trees. And I'll talk about shallow trees. But you essentially grow up and up and up on top of each other. Another way to think about this is that it's equal to the previous tree plus this tree. Right? It's like when you're doing a proof through induction, right? I guess induction is probably not the right word at all. But essentially, whatever the last iteration of the tree was, and plus the most recent learned tree. Does that sort of make sense? Boosting is kind of a hard concept, and we're learning it in 10 minutes. So it's going to be difficult if you don't know this already, especially if you don't know what a tree is already. It's going to be difficult. I feel a lot of confused energy coming at me. But when I took this in grad school, we spent many days on this, not 10 minutes.
Could we think of it as you build a tree, and what you learn from that tree, as you said, with the residuals, y minus y hat, you then use that knowledge. It's a bit like, you put your finger on the cooker and it hurt a bit, so you sort of learn not to do it. And if you're really stupid like me, you might do it 3 times, then work it out. Or you learn that 2 spoons of sugar was too much, you sort of tried 1.5, it's not enough, so you try a bit. And you learn, you remember what you learned, and then you turn up with your best model or function. So you get the perfect cup of tea or coffee for an American.
No, I'm a tea drinker.
Sorry.
No, yeah. You're close, but in your situation, you will just end up with the perfect cup of tea and put 1.5 teaspoons, right? Here, you would do 2, you would do 1, you would do 3, you do everything and combine them all at the end. So you're not sticking with just the last tree, you're taking the combination of all of the trees.
Okay.
Right, so you're close in your analogy, but we're not quite there.
Are you abusing notation there? Because I don't understand I'm getting hung up on what the plus operator is doing.
You're literally adding the values, so the tree. So I'm making a prediction. So y hat is the prediction for a single row of data.
Yeah.
And your row of data is the prediction from the first tree, plus the prediction from the second tree, plus the prediction from the third tree, the fourth tree, the fifth tree, the sixth tree, so on.
But if the prediction is a category,
Then it's so the category, you don't actually predict a category, you predict a probability, so you can add up your probabilities.
well, yeah, but what happens if you add them and they go to more?
There's a normalization step.
Okay.
Yeah.
So if you look at your errors, basically.
Yeah. Residual is another word for errors. Yeah. So at each tree along the way, you look at the errors and use that as the outcome variable for the next tree, which gets built on top of it. So it's an additive tree you add up. Since you're modeling residuals, you're able to, that's how you don't have to worry. You don't need to worry about normalization. Since you're adding up residuals, it's all going to sum up to be the right number. I know this is a very difficult concept. But essentially, you're allowing the tree to learn from its previous mistakes. Like for instance, let's say I fit my first tree, and I predicted your height very poorly, and I predicted your height very well. When I build my next tree, I'm going to pay more attention to you and less attention to you. And now you're still going to get good results because your first tree did really well. You're going to get good results now because your second tree did really well. Then I'm going to do my third tree. I'm still not quite good enough on you, so I'll boost you up a little bit. I'm still doing well on you, so I'll boost you down a little bit. Do the next tree. Now I've overcompensated, so I'll boost you back up and you back down. And that's how I get better and better, and I hone in on each of the data points. Does that make sense?
Got so many questions there.
That's natural.
A question about performance. So you said the random forest used to be like a leader in terms of performance, but now the
Boosting,
outperforming the random forest.
it definitely outperforms random forest now.
Most of the cases with those-
Yeah. Yeah, so XGBoost then became the darling of the Kaggle community. We shouldn't base everything on Kaggle, but it did become the darling of the predictive modeling community because it just is outrageously fast and excellent at doing predictions. Now, of course, there is the no free lunch theorem. There's no one best model for every situation, but in most situations, for pure predictive power, XGBoost is the winner. And there's lots of other algorithms, like there's something called the MARS algorithm, multivariate adaptive regression splines, which seems very similar to a boosted tree. Actually, there's a boosted MARS, which seems very similar, but it's slightly different. But XGBoost just ran away with it all. And I will say this, though. While random forest was all the rage in the States, there's something in Europe that was very popular called Cubist. And that's essentially partitioning your data and doing a regression at each node. I'm oversimplifying it. But Cubist was hugely popular in Europe. But show of hands, who's heard of Cubist? Not so many. So maybe it wasn't so popular here as people claim it is.
No, I've always been taught that until XGBoost, at the back, random
Yeah.
forest is your go-to algorithm.
Right. And you're from here.
Yeah, oh yeah.
Yeah. So maybe Cubist just wasn't as popular as people led me to believe. But it's supposed to be great from what I've heard. I've never actually used it, but people who use it love Cubist. So basically, you're hearing a lot of different algorithms here. It's all the same goal. Because once you're in a black box model, who cares if it's an XGBoost versus a Cubist versus a random forest versus Mars, right? Who cares what it is, whichever one predicts the best. Today we're learning about XGBoost.
You're saying XGBoost is a black box model.
Mm-hmm.
So you can't.
Good luck understanding what it's doing, and like you know what it's doing. Good luck figuring out once we start boosting. Good luck figuring out how you got to your prediction at the end. I know the math that went into it, but the splits, you're not going to know what the splits are. No, because we're going to fit 100 trees, each of which has 10 splits or 6 splits, right? Now you're looking at 600 splits and you're averaging and you're adding them all together. If you can figure it out, publish a paper, and you're going to win a Fields Medal. I'm not joking. That would be amazing. Yeah. I mark this day. Today's the day he's going to win a Fields Medal.
Remember, we're your friends.
Yeah. But you got to do it fast. You have to be under 40. Do you know that about the Fields Medal?
No.
So the Fields Medal is only awarded every 4 years, and you have to be under 40 to win it. Yeah, mathematicians. And since there is no Nobel Prize in mathematics, the Fields Medal is the top of the game. I don't know why they cut you off at 40, though. It seems kind of brutal. There is a Nobel. Technically, the Nobel Prize for Economics is the Bank of Sweden Nobel Prize.
Right, but there's also another big medal for economics which cuts off at 40.
Oh, really? What's the obsession of 40?
Paul Krugman's.
Oh, wow. All right. So far we fit a single tree. And that's great and all. But I'd like to see how well we did, actually. So let's fit one more single tree. I'm going to do a lot of copying and pasting now because I want to keep each thing separate. Feel free to just update the code in place, and I'll keep copying and pasting so you can see the history. Feel free just to modify in place. I'm going to say xg2. I want to know how well I'm doing. I saw my tree, but I want to see how well it did. So I'm going to say the eval metric is log loss. And my watch list is equal to the list train equals xg train. What I'm saying is, for the training data, which is what I'm training on, compute the log loss and tell me how well I'm doing. And I have a log loss of 0.58. What is log loss? Log loss is a cost function. When you're doing binary classification, it might be easy to say you got it right or you got it wrong. Right? It's binary. But it's actually better to say, how right were you? How wrong were you? There's a quote from a TV show. It's less wrong to call a tomato a vegetable than it is to call a tomato a suspension bridge. Right? How wrong you are matters. If I'm predicting that, what are we predicting now? Are we predicting hair color? Well, I forgot what we're predicting for this room. We didn't.
That's what we were doing.
Sure. We were using it as an input. Let's say I'm predicting the color of your shirt. So you're wearing, is that pink?
Yeah, something like that.
Let's call it pink. If I said that shirt is 90% pink and it's pink, that's great. But if I said that shirt is, I'm only saying it's 70% chance of being pink and it's pink, that's not as good. Let's talk about being wrong. Let's say that shirt has a 10% chance of being black. Hey, I did pretty good. If I say that shirt has an 80% chance of being black and it's really pink, that's terrible. So now I have a measure of how wrong I am rather than am I wrong or am I right. And there's a lot more nuance in there. So log loss allows us to do that. And if I'm correct in my memory, the formula for log loss equals, it is the true y times the log of p plus 1 minus y times the log of 1 minus p. And technically, we would do this. All right. What is y? What is p? Y is the true outcome variable, either 0 or 1. Right? Because remember, we have categorical data. We made them 0 or 1. In our case, historic, not historic district is 0. Is historic district is 1. P. P is the prediction. When you fit a binary model, you don't get back yes or no. You get back a probability. You get back percentages. So I'm saying the true value of y times the log of my predicted probability plus the opposite of what it was, so it's either going to be 0 or 1, times the log of 1 minus my probability. So let's say it was that for each given row of data, so this should technically have i's in front of it. This is for each row of data individually. So technically, we got this going. Right? So for any given observation, it was historic times the log of the probability that I predicted it was historic, plus 1 minus historic, which is just 0, and this zeroes out. So if I predicted, if it really was historic, I get this part. If it really wasn't historic, I get this part. And then it flips, going for the nose. And then you sum this up over all the rows of data, and you get a sense of how wrong you are. Do you want to be more wrong or less wrong? Less wrong. I know it's after lunch, but come on. So that's log loss. Let's not get hung up too much on log loss because we have a lot to do, and that can't be right. Do we only have half an hour again? All right, got to fly through, yes.
Quick question. In the code you say number of rounds equal to 1. What does that mean?
We're fitting one tree. We're not boosting anything. We're fitting a single tree. We haven't boosted yet. All right, let's go boost. Good segue. All right, so now we fit one tree. Let's fit multiple trees.
Are you going to push?
I'll push in a little bit. Yeah. I'm going to call this xg3. And instead of one tree, let's fit 100 trees. And you can see, look at that. My log loss is getting better. If each tree, thanks to the boosting, my log loss is getting better. So by adding together 100 trees, I have a log loss of 0.23 versus one tree which had a log loss of 0.58. Much better, right? Just by boosting. And again, the boosting was taking a tree, learning from its mistakes, and fitting another tree. Learning from its mistakes, fitting another, fitting another, fitting another, and then adding everything together. All right, that was awesome. What is it? Say it one more time.
So we get the average.
The average, no, remember, the trees are additive. They're not average. You add the trees up.
So the last one is the
No. So what you do is when you have your 100th tree, it makes a prediction which adds up the predictions from all the trees, and that prediction, so then you do the log loss on that prediction versus the true values. So you're doing the log loss on predicting on the training set, your fitted values. So that was pretty awesome, right? Should we instead do 300 rounds?
Yes, please.
Right? I'm going to copy and paste so you can see this. I'm just simply going to change this to 300. I'm still going to call it xg3. Yeah, I'll call it xg4. Why not? All right, look at this. Look at our log loss. It's getting better and better. I'm at 100 trees, finally got to there. And again, your results will vary a little bit. There's a stochastic process in here. Look at my log loss. It's down to 0.19. It's probably overfitting. I could keep boosting forever. Asymptotically, my log loss will asymptotically go to 0 as I keep boosting, as I keep adding iterations. Though 0.12 log loss, that's pretty awesome. But, and there's a but here. That's on the training data. Asymptotically, it's always going to get better on the training data. So you know what we need to do? Look at the validate data as we boost. Should we do that? All right. I'm going to go through it a little quickly. I'm going to copy and paste. I'll call this xg5. And in the watch list, I'm going to say validate equals xg val. And now we're getting both the training log loss, which will always get better, and the validation log loss, which, while it's getting better, still better than we did on our one tree, is going to eventually not get any better. So I'll push while we wait. All right, look at this. Our training data set kept getting better, but for validate, we might not be any better. So we can see this by saying XG5 dollar evaluation log.
For that log error, for that log badness, what do the off-diagonal elements of the contingency table, what kind of value would they have?
That would tell you, that gets into specificity versus sensitivity. You definitely want to look at your area under curve. We don't have time right now, but you would definitely look at the area under curve in this situation. Now this evaluation log shows you for each iteration, if I had done 1 tree, here's my log loss. If I had done 2, here's my log loss. It's not at 2, remember 2 is additive. So if I had done 3, which is additive, 4. But do we like looking at a table of numbers? No. What do we want to do instead? So we say digraph of XG5 dollar evaluation log. Digraph is a JavaScript library that's meant for plotting time series, but works with any ordered data, any sequential data. If we look at this, and I'll pull up my code again in a second, the green curve is my training data. It always gets better with each iteration. The purple curve is my validation data, and you can see at a certain point, it just stops getting better and may even start to get worse. So right around here, I think it's had enough. And we could go find the absolute minimum place for it, and that's the optimal number of iterations.
Janet, when you are mentioning validation data, did you do a 60-20-20 split and you still
I
have
did.
20 test data set?
I did 80-10-10.
Okay, fine. But,
Yeah.
okay, but
The test that's completely separate.
3 set. Okay.
Yep. All right. Okay. So what if, do we want to keep training once we've already hit like the optimal point?
For a bit, because it's going to be a bit stochastic, isn't it?
Right. So it's going to be a bit stochastic. So it might get worse, but it might get better again. So let's tell XGBoost to stop trying after it hasn't improved for a while. So I'm going to say comma, early stopping rounds equals 70. So I'm saying if it hasn't improved in 70 iterations, call it a day. Oh, look at that. It ran, it got to 200. By the time it got to 200, it was like, hey, it hasn't gotten better for 70 rounds. 130 was the last point. It was like the best we've seen. Let's stop and return back the 130th result.
So it's not recent memory, it's if you haven't got any better than your best in your...
In the past 70. In the past 70.
Yes.
And remember, so that means you're taking 130 boosts. You're not stopping at the 130th tree. You're saying you're going to take 130 boosts. So you still have 130 trees that all add up together.
Yeah.
And it's done. This way, because I could keep boosting forever, but at a certain point, like, hey, listen, stop if you haven't gotten any better. We don't have unlimited computational power. And we can look at this and say XG6 best iteration was the 130th. XG6 best score was, the best log loss we had was that.
Janet, the early stopping rounds parameter argument set at 70, is that like a good point, or did you just randomly pick 70?
So early stopping, there's entire textbooks written about early stopping. It's a hard problem to solve. And I've just done this so many times, like 70 looks nice.
Okay, so it's a good place for newbies to start.
Well, for this data set.
Okay, all right.
So
Right, okay.
I'm reluctant to say here's one place that's the best place for you to start. Because you read textbooks about this.
just wanted to ask in the log loss function that P was the probability that you write or that you write?
No, it's the prediction of your output. Remember, your outputs, your predictions are probabilities. I'm not saying you are historic. I'm saying you have a 90% probability of being historic according to my model. All right. So, the afternoon is a little harder than the morning, right? It's much harder content. Yeah. So, someone asked me earlier, I think blue shirt, I don't know your name actually. Marvin, thank you. It's the first name I've gotten today. Marvin asked about the depth of the trees. It went 6 deep. Were you the one who asked that?
Yeah.
So, what is the proper depth? Because when you have trees that are too deep, you might get overfitting. When you have trees that are too shallow, you don't get enough information. So, there's a hyperparameter called max depth. And we can set that. Now, it's the maximum depth. I'm not telling it to go to 6. I'm telling it don't go past 6. So I'm going to copy and paste again. Change it to xg7. And I'm going to say max underscore depth equals 8, the default being 6. You know what I'm going to say? 1,000 iterations. Now, each of my trees are being more complex. Well, they could be more complex, saying don't go past 8 as opposed to don't go past 6, which is the default. Typically, with boosted trees, you want short, stumpy trees, so you might have a max depth of 2 or 3.
Is that similar to M-try reinforced?
Yes. Well, no, M-try is how many times, yeah, that's split, number of splits, right? Yeah. Is it,
M-try
no.
number in random forest number of trees you set at 500, I think is default, isn't it?
No,
No?
that's entry.
Okay.
I thought M-try is how many columns to try at each split.
Yeah, how many variables you choose?
It is how many variables.
Yeah.
Well,
Oh, yes.
this is more similar to complexity in our part. I'm sure random forest has a similar split, but random forest is supposed to be parameterless, but it isn't. I think M-try is the number of columns to choose from randomly.
They say the idea is the square root of the number of variables you got.
That's another rule of thumb.
Yeah.
Yeah. Oh, look. Our best iteration was 134. Let's try that again with a max depth of 3. So basically, I'm saying the trees are much shallower. They're much simpler now. And look, we're going past 134 trees because the trees aren't learning as much each individual one, so it takes more trees to learn properly. We might hit 1,000. We might hit our limit and never got to our 493. It took 493 boosting iterations to match the performance of 134 boosting iterations when we had more complicated trees. I'm not even sure they matched. Let's look at this. XG $7 best score, best score versus XG's 8's best score. It looks like the tree with more depth but fewer iterations was better.
Is there something like a grid search function?
Question is there a grid search function? The answer is caret. Caret will do this automatically. The nice thing about caret is it's one interface. So it's the same exact commands for GlimNet as it is for XGBoost, as it is for Mars, as it is for Cubist, as it is for this. And it will do the grid search for you automatically. Now, let's be careful about grid search, though. Some people say you should make a grid and search over it. Other people say you should have a random search. And random search has proven to be much more popular lately than a grid search is. Because when you're doing grid search, if you have like 7 parameters, you're changing 1 and not the other 6. It's not going to make that much of a difference. It's more efficient to do a random search. But same idea.
Do you know how that works engineering-wise? Do the maintainers of Caret keep it up to date as new learners come out, or is there an interface specification for learners?
So the question was, does Carrot keep up to date? Yeah, so Carrot right now handles about 273 different types of models, and they keep it up to date. A new package comes out. If someone just, hey, Max, have you done the latest function? He says, sure. I know I've definitely had stuff written for me, and he'll do it. If Max hasn't done it yet, he actually made Carrot robust that you could write your own things to go take advantage of the infrastructure. That's it. Carrot is slowly being replaced by his new packages. He's splitting it up into the tidy models set of packages. So there's rsample, there's recipes, there's parsnip, and a few other ones to sort of replace Carrot. Yeah, parsnip. And so Carrot's still the gold standard right now, but he's slowly replacing it. For what? No, because it's Carrot. Yeah. There's a lot of puns in the R community. There's a lot of puns. Like, it's getting to a point there's too many puns. But yes, you would want to do a random search or a grid search, and you could program it automatically because all machine learning is just brute forcing your way through different parameters. So you could just make a simple for loop that went through a bunch of different parameter settings and did it all for you. However, it'd be much nicer just to use Carrot. It's built the for loop for you already. All right, any other questions?
So XGBoost is just one tree stacked on top of each other. Could you make a forest of boosted trees as well?
Can you make a forest of boosted trees? Let's find out. So before even going to forest of boosted trees, by the way, theoretically, not theoretically, in actuality, we've been doing trees of XGBoost. XGBoost could actually do linear models as well. You could change it to GB linear, and it'll do a penalized regression tree. How cool is that? You could do, actually no, sorry, it is a boosted penalized regression tree. But it doesn't work as well as the tree, penalized is I need to speak correctly here. It is a boosted penalized regression model. It's a linear model, or a logistic. But we're not going to show it today because we're almost out of time and because the trees do better than the linear models in this data. Let's talk about a random forest. XGBoost can do a pseudo random forest. It's not a true random forest, but it's similar. So what we're going to do is this. We're going to take XG8 and copy and paste. We'll call it XG9. We're going to take n rounds, and we are going to make it, we're going to do, let's leave it at 1,000 for now. Max depth we'll leave. We'll say subsample equals 0.5. Remember, when you do a random forest, at each split, you're randomly sampling the rows. What we're doing here, we're now saying for each tree, not each split, but each tree, randomly sample the rows. Comma, call sample underscore by tree equals 0.5. What this is saying is for each tree, not each split, but each tree, randomly choose only half of the columns. Comma, num parallel tree equals 10. Well, let's change our parameters. Let's boost it only 10 times, and we'll do 50 trees at a time. Sound fair? And when we do this, I am now fitting 50 trees at a time, so a little like mini forest, maybe it's the woods, the backwoods, and we are boosting each of those. So we're doing 50 trees at a time, boosted 10 times. And our log loss isn't super great. I've done this on this data set a lot. On this data set, in order to get the random forest to do even close to as well as a straight up boosted tree, I needed to fit, I believe, 50 trees at a time, boosted 100 times for 5,000 trees. And so for the amount of time that takes, I'd rather just do a straight up boosted tree on this data. So it's a pseudo random forest, not a true random forest. But it's pretty cool that we haven't even had the capability to do that. Now what we could do is, and we're not going to, it's not worth it on this data, there is an option, ncore, and that lets you use multiple cores on your computer. And if you're really into it, if you happen to have a GPU lying around, you could build XGBoost to work on a GPU and do it massively in parallel. Now, a question you should be asking, wait a minute. Aren't the trees built sequentially? How do you do that in parallel? Well, within each tree, remember, you have to do multiple splits. And for each split, you need to observe all the columns and figure out all the possible splits. That search can be done in parallel. Also, once you're down at the branches, you're recursively partitioning within a tree. You can do multiple searches in parallel. So each search can be in parallel, and each search and multiple searches can both be done in parallel. So if you throw this onto a computer with a GPU, you can get some significant speedups by doing it in parallel if you have big enough data. Of course, my laptop does actually technically have a GPU, but we're not going to do that today. XGBoost is an amazing, amazing algorithm. And I have to dabble in deep learning because it's all the rage. And I've done a lot of tests, and I can almost always get XGBoost on non-image and non-audio data and non-like census data. I can almost always, actually, so far always, got an XGBoost to perform better than deep learning. And XGBoost takes me a fraction of the time to code and a fraction of the time to train. Deep learning has its place, especially for audio and video and images, but for regular vector data, XGBoost is amazing and it's blazingly fast. And by the way, everyone talks about deep learning, they're so excited about the gradient. XGBoost, the G stands for gradient. It's the extreme gradient boosting. So let's not get all excited about the gradient being something new. Are there questions?
I'd like to ask a technical question about regression trees, but only if nobody else has got questions.
Anyone else have a question about trees? Regression trees or boosted regression linear models?
So specifically regression trees.
Okay.
My understanding is that each leaf, there's a little local linear regression model.
Not necessarily. There's some trees are built that way.
Yeah.
XGBoost, at each leaf, it just takes the average for a regression tree.
Okay, so when you jump from the cell in hyperspace that's represented by one leaf to the next, there will be a jump in the answer.
Yes.
Is there any variant on this technology that gives some measure of continuity with a more complex model or communication between the subcells? Or
Not that I'm aware of, but that doesn't mean it doesn't exist because there's so many variations of trees. Like there are some trees where each node is a linear model within the node,
yeah, that's what I was thinking.
right?
But then when you go to the next node,
It could be a different linear model.
yeah.
Yeah, and maybe there is something you're talking about because there's so many variations of this thing. You know what? Mars is kind of what you want. The multivariate adaptive regression splines. It looks like a tree, but the way it's built, each node is sort of a little more connected. So check out Mars, M-A-R-S.
That's available enough.
Yeah, and the carrot package does it nicely. Anyone else? I know we're closing in on the end here.
You run your model, you got it. How do you relate that back to your normal table?
Say it one more time.
How do you relate it? So how do you know? Your normal data that you've got, your rows,
Mm-hmm.
what variable do you use to relate that back to?
I'm not sure what you're saying here. My training data, your testing data?
Your model.
Yeah?
So when you train it on, what we're trying to find out here.
I'm trying to build a model that when given new data will do really good at predicting the true Y value. So our land test, we could use that, and you use this model to make predictions on land test. And the land test data happened to came with a true Y value, so we can see how well we did. But in reality, you might be building this for a credit score. Someone applies for a loan, and then this model predicts the probability of default. And hopefully you get it right and you don't ruin people's lives.
Is there a way to add weights for the different features? To pay more attention on?
Is there a way to add weights to the features, not to the rows, but to the features? And so technically when you're doing the splits, that's deciding the weights. Oh, I gotta show you something really important. That's right. I don't think there's a way to say, hey, pay attention to this thing. I could be mistaken, but I'm not that I'm aware of. But what you can do is this. Well, this is completely different from what you're asking, but you reminded me of something. xgb.var, oh, sorry, xg.plot.importance. this takes in as an argument xgb dot importance, which takes in, let's say, xg7. Feature names equals call names of land x train. And when you do this, this is supposed to give you back a variable importance plot. Oh, you know, I'm missing a parentheses, aren't I? There you go. A variable importance plot. And it tells you after the fact how important the variables were to the model. Think about it. You're doing 130 trees. Each tree is doing multiple splits. The more times a tree has been split on a certain variable, the more time a variable has been used on a split, the more important it is. So it tells you how important variables are after the fact. What you're asking for, I still don't think, not off the top of my head. But if you want to learn more about the parameters for XGBoost, you can do $xgb.train and see all the different options you have here. I don't think what you're looking for is in there, but remember we're talking about max depth? There are 7 hyperparameters you can tune on XGBoost for your grid search or random search. This will define what all of them are. All right, so this afternoon, as a wrap-up, we learned about a tree, about the idea behind it, how to do a single tree. We learned about boosting. We learned how to do boosting of XGBoost. We learned how to visualize it. We learned a variable importance plot. And we learned about all the different ways to do early stopping, validation sets. And we learned about all sorts of other good stuff of XGBoost. So with that, I thank all of you for surviving this long. Hope you had a fun time.